walking within dense star clusters, or wandering the dust lanes of the galaxy, where they prey on stars or swallow planets whole. Our Milky Way may harbor millions of black holes, the ultra-dense remnants of dead stars. But now, in the universe far beyond our galaxy, there's evidence of something far more ominous. A breed of black holes that has reached incomprehensible size and destructive power. Just how large and violent and strange can they get? A new era in astronomy has revealed a universe long hidden to us. High-tech instruments sent into space have been tuned to sense high-energy forms of light, X-rays and gamma rays that are invisible to our eyes and do not penetrate our atmosphere. On the ground, precision telescopes are equipped with technologies that allow them to cancel out the blurring effects of the atmosphere. They are peering into the far reaches of the universe and into distant cauldrons of light and energy. In some distant galaxies, astronomers are now finding evidence that space and time are being shattered by eruptions so vast they boggle the mind. We are just beginning to understand the impact these outbursts have had on the universe, on the shapes of galaxies, the spread of elements that make up stars and planets, and ultimately, the very existence of Earth. The discovery of what causes these eruptions has led to a new understanding of cosmic history. Back in 1995, the Hubble Space Telescope was enlisted to begin filling in the details of that history. Astronomers selected tiny regions in the sky between the stars. For days at a time, they focused Hubble's gaze on remote regions of the universe. These Hubble Deep Field images offered incredibly clear views of the cosmos in its infancy. What drew astronomers' attention were the tiniest galaxies, covering only a few pixels on Hubble's detector. Most of them do not have the grand spiral or elliptical shapes of large galaxies we see close to us today. Instead, they are irregular, scrappy collections of stars. The Hubble Deep Field confirmed a long-standing idea that the universe must have evolved in a series of building blocks, with small galaxies gradually merging and assembling into larger ones. You can see evidence of this pattern by looking out into the universe. Many galaxies are gyrating around one another. Some are crashing together, others ripping each other apart. Gravity calls the tune as these galaxies draw together, exchanging stars and gas, and over time, merging to form larger composite galaxies. This came to be known as the hierarchical picture of cosmic history, in which the universe evolved from the ground up, with its structures growing larger and larger over time. A team operating at the Subaru Observatory atop Hawaii's Mauna Kea volcano examined one of the deepest galaxies known, whose light has taken nearly 13 billion years to reach us. It was a messenger from a time not long after the universe was born. This object is known as a quasar, short for quasi-stellar radio source. A small region in its center is so bright that astronomers believe its light is coming not from a collection of stars, but from a single object of at least 1 billion times the mass of our Sun. This beacon is generated by gas falling onto the object and heating up to extreme temperatures. The only thing known to generate this much power is a swirling cauldron where space suddenly turns dark as it merges into a giant black hole. For astronomers, the question was, how did this black hole get so big so early in the history of the universe? It likely got its start in an early generation of stars, often known as population 3 stars. Made up of hydrogen, they are thought to have been hundreds of times the mass of the Sun. These giant stars burned hot and fast and died young. A star is like a cosmic pressure cooker. In its core, the crush of gravity produces such intense heat that atoms are stripped and rearranged. Lighter elements like hydrogen and helium fuse together to form heavier ones like calcium, oxygen, silicon, and finally iron. When enough iron accumulates in the core of the star, it begins to collapse of its own weight. That can send a shock wave racing outward that literally blows the star apart in a supernova. At the moment the star dies, if enough matter falls into its core, it can collapse to a point, forming a black hole. The first generations of stars and black holes burst onto the cosmic scene in a time of incredible turbulence. Within primordial gas clouds, stars were being born in dense knots. They gave rise to black holes that began to swallow more and more matter. A computer simulation of the early universe shows just how quickly these voracious monsters were able to grow. The project, by scientists at Carnegie Mellon University, was designed to recreate a region in the early universe that measured over 100 million light-years on a side. It shows what took place in the first 1 billion years of cosmic history. This virtual universe is set in motion by equations describing the properties of gas, the energy released in starbirth, and the outward motion of time and space. The result? An intricate cosmic web, with gravity drawing matter into filaments and knots, like a vast tangle of interconnected spiders' webs. Inside the densest regions is where the largest galaxies and black holes grew. Here, circles indicate the appearance of black holes deep in the data. As they gain weight by eating up their surroundings, the circles grow larger. A few in the largest galaxies reach ultra-massive proportions, billions of times the mass of the Sun. These black holes were not just swallowing gas. The orbiting Chandra X-ray Observatory was dispatched to look into distant galaxies for black holes on growth spurts. Scientists looked for pockets of gas and stars glowing hotly in X-ray light. What Chandra found was that the core of some distant galaxies contained hot pairs, twin supermassive black holes drawn together by gravity. Black holes by nature resist this dark marriage. As the two approach each other, they go into an orbit that could last virtually forever. To learn what allows them to merge, we go back to the ideas developed by Albert Einstein. He said that when massive bodies accelerate or whip around each other, they literally disturb the fabric of space, causing it to ripple like a disturbance on a pond. When these ripples move outward, they carry with them the energy of the pair's orbit, causing them to spiral closer. When this dance of death comes to an end, that's when the pair joins together to form a larger black hole. That moment may be approaching for a quasar called OJ-287 at 3.5 billion light-years away. Flare-ups in the surrounding region have led astrophysicists to conclude that another black hole is flying around it. By measuring the giant's gravitational hold on its companion, astronomers estimate its mass at 18 billion solar masses. For a time, OJ-287 was the largest black hole ever detected. It no longer is. Deep in the heart of the Coma galaxy cluster, a mere 321 million light-years away, lies a giant elliptical galaxy known as NGC 4889. Astronomers used several large telescopes to measure the speed at which stars are orbiting around the center. They used that data to calculate the mass of the central object. A whopping 21 billion solar masses, give or take a few billion. Theoretically, there are no limits to how much weight a black hole can gain. And yet, even the largest black holes and their host galaxies seem to obey limits. What holds them back has to do with the way clusters of galaxies evolve, a pattern long noted by scientists. This computer simulation shows the evolution of a galaxy cluster in the early universe. The gravity of the entire region draws small galaxies by the thousands, along with great streams of gas into the center. So why doesn't the central galaxy and the black hole that resides within it capture all this matter? Why don't they swallow the entire cluster? You can see the answer in a region called MS-0735. At 2.5 billion light-years away, it appears in visible light to be a typical galaxy cluster. In X-ray light, you can see that it's enveloped in a cloud of hot gas measured at nearly 50 million degrees. Hollowed out of this cloud are two immense cavities up to 600,000 light-years across. That's enough room in each to stuff 600 galaxies the size of our Milky Way. Now add in a radio image of the cluster. You can see two vast streams of matter pushing out from the center. That's a giveaway that the cavities were formed by an eruption in the core of the giant central galaxy. Two jets shooting out of a central black hole have launched blast waves that plowed through the gas that makes up the intergalactic medium. The energy it took to carve out these X-ray cavities is remarkable. The equivalent of several billion supernovae, according to one calculation. In fact, MS-0735 has been referred to as the largest single eruption recorded since the Big Bang. It was generated by a black hole that weighs in at around 10 billion solar masses. Black hole jets like this have been seen all around the universe, including in our own cosmic neighborhood. This is the famous M87 galaxy, at the center of the Virgo galaxy cluster, around 50 million light-years away. Astronomers have been intensively studying the black hole that lurks in its heart, and recently estimated its mass at 6.6 billion solar masses. It powers a pair of high-powered jets that are plowing through the galaxy. But how does a black hole, a creature famous for hiding in the dark, emit this much energy? Think of a black hole as the eye of a cosmic hurricane, kept rotating by all the stars, gas, and other black holes that fall into it. As this matter flows in, it forms a spinning donut-like feature called an accretion disk, which works like a dynamo. The spinning motion of the disk generates magnetic fields that twist around and channel some of the inflowing matter out into a pair of high-energy beams or jets. How much energy depends on the black hole's gravity and how much matter has already crashed through the event horizon. Is this just another frightening spectacle of nature? Or is it part of a more profound process at work? The largest black holes in the universe probably rose between 10 and 12 billion years ago, the age of the quasars. By releasing energy in the form of jets, they heated up their surrounding regions. This prevented gas from collapsing into the central galaxy and allowed smaller galaxies on the periphery to form and grow. But the impact of the black holes did not stop there. This Chandra image of the Hydra A galaxy cluster shows the same immense hot cavities glowing in X-ray light, as well as a jet blasting out of its central galaxy. Gas along the edge of the jet was found to contain high levels of iron and other metals, probably generated by supernova explosions in the center. By pushing these metals into regions beyond, a black hole seeded more distant galaxies with the elements needed to form stars in solar systems like ours. The black holes in these more remote galaxies then seeded their own environments. This is what might be happening in Centaurus A, also known as the Hamburger Galaxy. In X-rays, you can see a jet erupting from the center. Peering through the dense dust lanes that dominate our line of sight, astronomers have come to believe that it's actually two galaxies in the act of colliding. This computer simulation shows the effect of such a merger on black holes. As the two galaxies pass by each other, the pull of gravity disrupts their spiral shapes, forcing huge volumes of gas into their cores. As the black holes begin to feed, they emit blast waves that push much of the loose gas out beyond the boundaries of the new galaxy. In the final steps of this cosmic dance, the two black holes merge and emit one final blast. To think that our Earth, our solar system, ourselves, are the beneficiaries of these faraway monsters. The largest black holes have played dual roles in a great cosmic struggle. They are the product of gravity's relentless inward pull, the force that has drawn matter into galaxies, clusters, and the structures they form. But with their incredible power, they emit energy that pushes back on gravity. In so doing, these strange and powerful objects have become the master architects of space and time.